Welcome to Unit 11. Unit 11 discusses concepts related to climate, climate change, and the depletion of the ozone layer. We're going to begin by looking at the Earth's atmosphere. Here is a picture of the Earth's atmosphere from space. You can see how it gets hazier as you move out, if you will. If you look at the atmosphere, you have the troposphere, which is near the surface of the Earth. It regulates energy flow and weather at the surface. It gets colder at higher altitudes. Air mixes vertically, so pollutants at the surface rise in 1 to 2 days. And natural greenhouse gases at this level absorb some heat like an insulation blanket. Above the troposphere, we have the stratosphere. The stratosphere is warmer at higher altitudes because ozone, which is O3, absorbs radiation. There's little mixing in this layer, so pollutants are trapped there indefinitely. And precipitation does not come from the stratosphere. Precipitation comes from the troposphere. If you look at the graph here, it shows the temperature of the atmosphere as a function of altitude, and you can see how, where'd my marker go? There it is. We start warm at the surface, and then we cool to the top of the troposphere, and then as we go up in the stratosphere, we warm back up. Without the troposphere, the Earth would be about -1 degree Celsius rather than +14. So what happens with the radiation? 30% of incoming solar radiation is reflected back into space. The 70% is absorbed by the atmosphere, ocean, and land. So here we have the sun, incoming solar energy. 25% is absorbed by clouds and atmosphere. Some of that is reflected from the clouds and the atmosphere. There's also some that gets to the surface. 45% is absorbed by oceans and land. That's what creates weather. We have reflection from the surface at 5%. We have re-radiated energy from the surface. There's the retaining greenhouse gases. We have re-radiated energy from clouds and atmosphere, such that the total reflected energy is 30% and the output infrared energy is 70%. Here is another view of the same process. This one also outlines the greenhouse effect. We have sunlight coming in. So if we look at bullet point number 1 here, solar radiation passes through the clear atmosphere. The incoming solar radiation is about 343 watts per square meter. Going down to number 2, the net incoming solar radiation, so some's reflected, so net we have 240 watts per meter squared. As we said, some is reflected. That results in 103 watts per meter squared. Bullet 4. Solar energy is absorbed by the Earth's surface and warms it. That's 168 watts per meter squared. Bullet 5. Some of the infrared radiation is absorbed and re-emitted by greenhouse gas molecules. The direct effect is the warming of the Earth's surface and troposphere. That results in the surface getting more heat from an infrared radiation is emitted again. Some of the infrared radiation, bullet 6 here, passes through the atmosphere and is lost in space. The net outgoing infrared radiation is 240 watts per square meter. It's this trapping portion here that is the greenhouse effect. It's documented. We've done measurements. The climate has changed. Atmospheric temperature is going up. Since 1850, we've been making direct measurements of the atmosphere temperature. At this point, we've had an increase about 1 degree Fahrenheit since 1885. We can go back further, right, and get a historical view of the Earth's temperature. We can get this from looking at the fossil record, rock records, ice cores, many different things. The top graph here shows the local temperature change in degrees Celsius. You can see it fluctuates pretty well. The middle graph here is methane concentration, which is on the right axis here. Also has fluctuated a lot. And the bottom graph here is carbon dioxide, either on the left or the right. And the bottom axis is age in thousands of years before the present. So 0 would be today, because that would be 0 years before present. Notice where there's a peak in temperature, there's also a peak in methane and carbon dioxide. When temperature's gone down, carbon dioxide's gone down, and now it's going back up a little bit. Well, in the past 20,000 years, it's gone up a bit, I guess I should say. Right. So, as we noted, there's a correlation with the CO2 and methane concentrations between those two and the temperature. Right. As I mentioned, we can look further back based on indirect measurements. We can't go back 10,000 years and take a measure of the temperature with a thermometer, so we use things like ice cores from Greenland and Antarctica in order to determine what was going on at that time in climate-wise. We can look at these ice cores and quantify the gas content, the trapped methane and CO2, and the temperature based on I think that's supposed to be isotropic concentrations that were incorporated from clouds. So the rain in the clouds had some sort of methane and CO2 content. When it came down and got incorporated into the ice core, the methane and CO2 remained fixed at what they were in the cloud. Right. So here's another graph of CO2 concentrations. Direct measurements were made from 1950. Before then, we have ice core data, proxy data, in parts per million, and we can see a marked increase. See the fluctuations in the direct measurement? That is due to annual fluctuations. Sometimes it goes up, sometimes it goes down based on what's happening in the weather, climate-wise. You know, winter is going to have a different CO2 concentration than summer. Here we have a graph of CO2 on the left. That is the red line. And we have temperature difference in the blue line on the right. And 0 is the 1960 to 1990 baseline. On the bottom axis, the x-axis, we have years before present, so 0 would be today, if you would, and then we go back in time. And again, notice when the CO2 goes up, the temperature goes up. When CO2 goes down, temperature goes down. There's a very nice correlation between these two effects. Look here. In July 2005, carbon dioxide exceeded 380 parts per million. From 1000 AD to 1850, CO2 never exceeded 300 parts per million. Look at that. Here we have a graph of CO2 concentration in parts per million as a function of year from 1958 to 2000. And again, you can see the annual variation, but still we have an upward trend. So we've seen that there is this annual variation in the CO2 concentration. Why is it higher in the winter in the northern hemisphere? If we look, the vertical axis is CO2 concentration, the horizontal is the year, the winter concentration is the gray line, and the summer concentration is the orange line. So there is this annual variation, winter to summer. What's going on? It's all about the plants. In the winter, deciduous plants like oak trees or maple trees lose their leaves, and therefore the carbon uptake is reduced. Because the carbon uptake is reduced, that leads to a higher concentration in the winter when the trees don't have their leaves. Where are we storing carbon? We have a lot stored in terrestrial biosphere, living and dead things. A lot is there. There's some in the atmosphere. There's also a ton stored in the ocean and some in fossil fuels. And we can exchange between the various places through example, combustion of fossil fuels puts it in the atmosphere. Respiration and photosynthesis take it out of the atmosphere or put it back into the atmosphere from the biosphere. And then we have an atmosphere-ocean exchange that goes both ways as well. Here we have an odd-looking map of the world. The circle indicates, or the size of the circle indicates how much that particular area of the world releases in carbon dioxide emissions as of 2009. The smaller the circle, the fewer the emissions. So it's not surprising that there's very little in Africa or South America from that standpoint. Probably also not surprising that China is very big, as is the US. India and Russia are also big emitters. If we look at the US, where does the CO2 come from? We have natural gas. Natural gas is primarily used for residential, commercial, and industrial purposes. Right? Of the 5,682 million metric tons of CO2 produced in 2002, 2,206 of them were residential commercial. 1,674 of them were industrial, and transportation resulted in 1,850. Notice all of the CO2 for transportation came from petroleum products. We burn gas. Not a surprise there. Industry had a little bit from coal and a little bit from petroleum and a little bit from natural gas.